Hello everybody. Today I would like to give an introductory lecture on hydrogen cost modeling across the value chain. Before we start, let's have a look at the milestone in the hydrogen value chain. This ship, called the Suiso Frontier, is the world's first hydrogen tanker, which has a gross tonnage of 8,000 tons, a 1,250 cubic meter storage tank, which is able to carry liquefied hydrogen at 0.125% of its original volume when it was in its gas state. This ship undertook a 2-week voyage to transport the liquefied hydrogen from Victoria, Australia to Kobe in Japan early this year. This is a hydrogen energy supply chain, a new project being developed in Victoria State with the support of Japan. This project has received $100 million from the Victorian and federal government. Australia shipping the world's first liquid hydrogen to Japan marked a milestone in the looming transformation of hydrogen export. This project helps us to understand the whole hydrogen value chain, so I will explore this project more later. This lecture will cover the following parts. I'd like to start with the introduction of the value chain, and then the cost models in each sector. Next, we will learn about the project. Finally, let's explore the hydrogen opportunities. The hydrogen value chain can be broadly categorized into 3 parts. In the upstream, it is the production of hydrogen. The large majority of hydrogen produced today, about 95%, comes from the fossil fuels. Around 5% of the hydrogen produced today is green hydrogen. Only 0.1% of the total hydrogen production today derives from water electrolysis, which is the most common method for green hydrogen production using renewable power sources. In the midstream, the storage and transportation of hydrogen. Since hydrogen is highly flammable, it takes up a lot of space and often requires blending with natural gas to safely distribute using existing gas pipelines. Currently, hydrogen is distributed through pipelines, liquefied hydrogen tankers, or high-pressure tube trailers. In the downstream, the usage of hydrogen. These uses include electricity generation, heating, and a few different modes of transportation. Let's start with the hydrogen production. We will discuss the method to produce hydrogen, Electrolysers Technologies, and the cost. Then we will focus on the cost model. The color spectrum is intended to characterize relative carbon intensity. So the green hydrogen is formed through the processing of hydrocarbons, where there is an unmanaged byproduct of carbon dioxide. For the blue hydrogen, it's formed through the same process as gray, black, or brown hydrogen, but where the carbon dioxide byproduct is captured and secured via the appropriate carbon capture storage technology. For the green hydrogen, it formed via electrolysis of water using renewable electricity sources and having no process-related carbon emissions. This picture shows the green hydrogen production set using wind or solar power. This is a real project that utilized the offshore wind power. A very important device in the whole value chain is the water electrolysers. They are electrochemical devices used to split water molecules into hydrogen and oxygen by passage of an electrical current. The cell is the core of electrolyzer, and it is where the electrochemical process takes place. The stack has a broader scope, which includes multiple cells connected in series, spacers, seals, frames, and end planes. The system level includes equipment for cooling, processing the hydrogen, converting the electricity input, treating the water supply and gas output. Purified water is fed into the system through circulatory pumps or also by gravity. The water then reaches the electrodes by falling through the bipolar plates and through the porous transport layers. There are 4 types of electrolyzer. Alkaline and polymer electrolytic membrane are already commercial, while anion exchange membrane and solid oxide, now at lab scale, promise a major step forward. The principle of water electrolysis is simple. It allows the construction of different technological variations based on the various physical, chemical, and electrochemical aspects. Here are the typical system design and the balance of a plant for each type of the electrolyzers. When we look at the cost breakdown for these 2 types, they share the same cost structure at the system level, but quite different at the stack level. This is a summary of the benchmark cost of electrolyzer. The impact of a manufacturing scale and continued research and development are expected to support a rapid cost reduction curve for the electrolyzers. It should not be expected that continuous cost declines comparable to those industries can be achieved for the overall system. But in the longer term, it is expected that price reductions will occur in all categories identified, rather than occurring in a specified area. Let's conclude what is included in the production cost. The first one is capital expenditure. The second one is variable and fixed operating expenditure. The third one is hydrogen compression cost. Here, the example, you can see what is included in the CAPEX or OPEX. The cost of different hydrogen production methods vary widely due to factors such as technology and fuel costs, carbon tax, and load factors, and volume of development. This is an example of a cost breakdown. Green hydrogen production costs are driven by the capital expenditure, which is the cost of an electrolyzer. Reducing electrolyzer costs and improving utilization rates can lead to lower the green hydrogen production cost. Markets with a high level of renewable penetration have favorable conditions for development of electrolyzers. As the level of renewable output continues to increase and the power price are expected to decline. In terms of the blue hydrogen production cost, the CAPEX covers the cost of a facility that uses SMR technology, where the variable OPEX costs are driven by the future price for natural gas. With large-scale development, innovation, and more efficient supply chains, there is an opportunity to reduce the CAPEX and CCS costs. Until now, we understand the components of the hydrogen production cost from cell level, stack level, to system level. Moreover, different ways of production can lead to different costs. Now, let's have a look at the cost trend to have a larger picture of the hydrogen future. The blue hydrogen may be cost competitive for only a limited period of time, where the blue hydrogen is cheaper today than the green hydrogen made from solar or wind electricity. The situation should be reversed by 2030. Bloomberg expects that the renewable hydrogen to be cheaper by 2030 in all modeled countries, even those with cheap gas, such as the United States, and those with pricey renewable power, such as Japan or South Korea. Even the grey hydrogen, which is today's dominant form, made from fossil fuels without CCS, could cost more than the green hydrogen by 2030 in 16 of the 28 countries that Bloomberg has modeled. This will unleash a tectonic shift in the hydrogen market. The next stage of the hydrogen value chain will focus on the storage and transportation. We'll discuss the storage options and the cost comparisons of all available transportation. At an export terminal, for example, hydrogen storage may be required for a short period before shipping. Hours of hydrogen storage are needed at the vehicle refueling stations, while days to weeks of storage will help users to protect against a potential mismatch in hydrogen supply and demand. Much longer term and large storage options will be required if hydrogen were used to bridge major seasonal changes in electricity supply or heat demand, or to provide system resilience. The most appropriate storage medium depends on the volume to be stored, the duration of storage, the required speed of discharge, and the geography available of different options. In general, however, the geological storage is the best option for large-scale and long-term storage, where tanks are more suitable for short-term and small-scale storage. Today, hydrogen is usually delivered in compressed gas or liquid form. The majority is either produced and consumed on-site, it's about 85%, or transported via trucks or pipelines, that's around another 15%. In the future, the balance between these options could change and new alternatives could emerge. The competitiveness of the different options will depend on the distance over which hydrogen is transported and on scale and end use. Long-distance transport would enable the export of hydrogen from low-cost production regions to high-cost ones. The overall cost of delivering hydrogen will vary according to the infrastructure available in the exporting and importing countries, transmissions and distribution distance, the method of transport, and end-use demand, despite many uncertainties around most of these cost components. IEA analysis suggests that for inland transmission and distribution, hydrogen gas is a cheaper option for distance below around 35 kilometers. Above this distance, ammonia pipelines would be the cheaper option. Comparing transport using pipelines and ships, transmission and distribution of hydrogen gas by pipeline is cheaper for distance below or around 1,500 kilometers. Above this distance, ammonia transport by ship, which are broadly similar in terms of their full cost, became cheaper delivery options. The transport and the use of ammonia or some long-distance hydrogen may, however, give rise to potential safety and public acceptance issues, which could limit their applications in some situations. And when we compare the delivered hydrogen cost with the domestic one, we can see that the cost of a transport from Australia to Japan could represent 30% and 45% of the full cost of hydrogen, yet imports of the electrolytic hydrogen could still be cheaper than the domestic production. Moreover, hydrogen imports could be cheaper than domestic production for a number of countries, especially if ammonia can be used by final customer without the need for reconversion back into hydrogen. By 2030, assuming at-scale production and transportation infrastructure, hydrogen could be shifted from locations such as Australia, Chile, and Middle East to projected demand center at a cost of $2 to $3 per kilogram of hydrogen. This cost, coupled with very low hydrogen production cost, unlocks demand in many key sectors at a point of usage. We understand that at each state of a value chain, there are many options. So for the different hydrogen demands, there are variable value chains. For production and distribution, these types of value chain are emerging. For the larger scale hydrogen off-takers that are in close proximity to favorable renewables or gas, and the carbon storage sites will use on-site production. The total cost would reach $2 to $3 US dollars per kilogram. The smaller off-takers, for example, refueling stations or households, will require regional distribution, include the production, conversion, and distribution cost. The total cost would reach $3 to $5 US dollars per kilogram. In region without optimal resources, both large and small off-takers may rely on hydrogen imports. So the total cost would reach $2 to $7 US dollars per kilogram. The final stage of the value chain is the usage of hydrogen. The major utilization is for transports, and other may use it as a fuel for the industry. The potential use of hydrogen for transport depends on the types of the vehicles. For the light vehicles, the heavy vehicles, the haulage vehicle, the heavy rail, hydrogen can offer operating flexibility, but it's not commercially viable. For the ferries, marine shipping, and aviation, there are high dependence on hydrogen because other alternatives may not be useful for long range and large scale uptakes. This table shows the opportunities and the challenges of future deployment for different types of transport. Another main use of hydrogen is as a fuel for industry. Australia has extensive natural gas networks to transmit gas from the source to distribute to customers. This section explores the opportunity to utilize the existing assets to cost-effectively deliver hydrogen and stimulate early hydrogen demand. Hydrogen blending concentrations above 50% are not currently considered feasible in existing distribution networks due to increased impact on safety, leakage, and material integrity. The only feasible alternative to reach blending concentration above 50% is to construct a dedicated hydrogen network over the existing national infrastructures. Blending hydrogen into existing natural gas distribution network at low concentrations, less than 10% hydrogen by volume, is generally considered viable without significantly increasing risk associated with utilization, like overall public safety or durability and integrity of existing natural gas pipeline network. Like this one, the combined heat and the power is the combined heat and the power is simultaneously production of electricity and useful thermal energy from a single source of energy. Hydrogen based on this one would likely to be based on fuel cell technology with an efficiency approaching 70% of the electricity yield. This opportunity is generally more attractive in cooler climates where the heating load is significant. Compared with natural gas with CCS and biogas as a flexible generation option, hydrogen may be cost competitive, particularly at low load factors. Moreover, whether hydrogen-based power generation for load balancing can compete on price against natural gas depend on the regional hydrogen, natural gas, and carbon dioxide prices. We have learned about the whole hydrogen value chain. Now we turn to the cost model. The levelized cost of hydrogen can be drawn from the capex operation and the maintenance cost per annual production of hydrogen. The chart shows that the levelized cost of hydrogen is the highest when using the grid electricity, for which our price series include either all or a reduced amount of a policy cost. Dedicated offshore connection reduce the levelized cost, but also increase the fixed cost elements of the total cost due to the lower load factors. Using the curtailed electricity does not incur electricity cost, but see significantly higher fixed cost due to the lower load factors. Technologies that have a higher upfront cost see large impacts. This table provides a summary of the model's output in each value chain segment. These figures help to understand the cost of hydrogen per unit. The levelized cost of hydrogen can be one of the metrics to assess the economics and commercial viability of a project, or to understand its cost competitiveness compared to other energy sources or projects. Next, I would like to share a hydrogen supply cost analysis tool. This tool is based on an Excel workbook to model the hydrogen output and costs involved in the production of a green hydrogen from solar, wind, or combined solar and wind power plants in Australia. It includes a levelized cost analysis and a cash flow analysis. We can see from the tool inputs, it has the system settings, electrolyzer parameters and costs, the battery parameters, as well as the power plant settings. The result will reflect the capex on the operating cost for electrolyzer and power plant. And this is quite clear to see the cost breakdown for each segment. This sheet contains the detailed cash flows required for the calculation of the net profit, return on investment, and payback period. If you are interested in this tool, you can turn to this website to check its user guide. Next, we will look at a project that's shown in the beginning of the lecture, the hydrogen energy supply chain. It is the world's first hydrogen energy supply chain project that aims to safely produce and transport clean liquid hydrogen from Australia's Latrobe Valley in Victoria to Kobe in Japan. The key objective of the pilot project is to demonstrate an end-to-end supply chain between both countries. The value chain includes the hydrogen production, storage, transport, the transport including the load transport and the shipping transport. In stage 1 and stage 2, the hydrogen is produced in Latrobe Valley by gasification and refinement. In the stage 3 and stage 4, through road transport in high-pressure tube trailers, hydrogen is transmitted to the port of Hastings to be liquefied. In stage 5 and 6, from port of Hastings, the liquefied hydrogen will be held in the storage and loaded onto the Swiss frontier to Japan. Hydrogen will play a crucial role in global efforts to reach its net zero target for 2050. It could help decarbonization efforts in a number of sectors, but needs investment and policy support to establish demand, increase scale of deployment, and reduce cost. Here are the 4 value chains that is going to be happening in very near term. The 4 value chains are not independent, as developments in one will benefit others in realizing cost reductions and innovation. Furthermore, within the same region, there could be opportunities to exploit the synergies between them. For example, for truck fleets operating between industrial clusters and along transport corridors, reaping the cost benefits of economies of scale in hydrogen supply and distribution is likely to require the cumulative demand of several sectors in a region, not one application alone. And for example, a growing hydrogen network for vehicle refueling could help launch flexible low-carbon power generation. Success in each of the value chains will help provide conditions for success in others. This tool is called Australia's Hydrogen Opportunity Tool, and this tool provides free access to geoscience data and tools for mapping and understanding the potentials for hydrogen productions in Australia. If you feel interested, you can check the website. To conclude this lecture, the cost of a different stage of a hydrogen value chain could have a significant impact on the final levelized cost of any hydrogen project. Hydrogen supply chains will need to be able to access financially based on an international outlook and the largest possible markets for scale up. Overall, the potentially crucial roles of hydrogen is increasingly recognized around the world. Thank you for listening to the lecture.